this video is going to specifically look at environments in which sediment is deposited that can later be lithified to create a sedimentary rock. So we'll look at kind of each environment and a little look at the sediment or the sedimentary rocks that are left behind. So glacial environments carry all sizes of sediment. So the sorting is actually very, very poor by the time it's over. The sediment that's left behind is what's known as till, and we'll look at glacial environments a little bit closer at the end of the semester. But where you find sediment is along the edges where it's scraping up against the rock. This is creating a lateral moraine, and when those run together it makes a medial moraine, but this is where that sediment's coming from. So it carries it downhill as the glacier flows and moves down, but eventually the glacier is just going to melt, and when it does, it just leaves piles wherever it happens to be. On the right is an example of a bit of sediment. That's a boulder. This is called a glacial erratic. This is actually in Central Park in New York City. So this is a piece of granite sitting on top of the Manhattan schist. The schist is a metamorphic rock, and that granite came from hundreds of miles to the north, which is pretty impressive. A desert environment is going to tend to form sandstones, because in a desert environment this tends to be kind of wind dominated in terms of deposition. Now, in terms of erosion, water is still really important, but for deposition it's mostly wind moving things around in these cases. Sand size or sometimes silt sized particles, and so when you have these beautiful sand dunes you tend to get cross beds. So this next picture is of the wave. That's how we started the clastic rock video. Beautiful swooping cross beds of the Navajo sandstone. And you can tell that the environment's changing from really dry to a little bit wetter based on the color. It's all a quartz rich sandstone, so it's all in arenite, but you've got where super quartzy, but there's layers in the middle where that quartz is actually held together by hematite. That's a good indication that you've got oxidation, which means you have extra water in those periods of time. So not only can we tell the direction of the wind blowing, we can also tell how humid it was too. Now, Playa Lake is a lake that holds water when it rains, but when it stops raining, there's nowhere for the water to go, but it doesn't have anything extra coming in, so it just dries up. So these are great places to find evaporite materials. So I've already shown you an example of the Bonneville Salt Flats in Utah, but this is the Wilcox Playa in southern Arizona. You can see just how white it is. That's from all that salt and gypsum that's deposited. On the bottom is actually a really cool salt mine in Poland. It's apparently really famous. Everything you see in this picture, minus the people and the lights, is carved out of salt. This is one of the longest used mines in the world. They were actually mining salt out of here back during the medieval period. Back in the day, salt was actually very important dietarily, just for your diet, and to preserve meats and food. And so Roman soldiers were actually paid in salt. That's why when you get your paycheck, we call it a salary. It comes from the same term as salt. River environments show up a lot. So these fluvial or river environments are going to form lots of different types of rocks, sedimentary rocks. So mudstone is going to, like you see here, is going to be created when fine sediment is deposited in floodplains around rivers. Coarser sand-sized sediment travels along the river bed to create sandstones, often with little bitty cross beds or ripple marks. And fast-moving rivers carry cobbles or sometimes even boulders, and that's going to create conglomerates. One of my very favorites is the alluvial fans. So alluvial fans form where fast-moving streams reach a mountain front and empty onto a flat plain. These form an apron of sediment that is mostly gravel-sized, and it likely forms conglomerates or even arco-sandstones. So little bit of tumbling down the river just to kind of knock the edges off, so it's not quite a breccia. But it doesn't weather that much. You don't get a lot of weathering out of it because the material is coming directly from that mountain front. So your sandstone still tends to have a lot of those easier to weather minerals all mixed up in it. This alluvial fan you see is in Death Valley. Super famous area. And you can see these little stream channels where it all comes out and empties off and deposits sediment. Down at the bottom here, those are salt deposits from the evaporating water below it. On the right is a picture of Papago Park. The Papago Buttes are actually formed from alluvial fan. So that's why they look tilted over. They haven't actually been tilted. That just shows you the bedding of from the alluvial fan as it was being deposited. Now these are in the middle of nowhere, so where's the mountain front? The mountain front was actually McDowell Mountains. Things have just moved quite a bit since these were forming. Beautiful example of Tafoni here. So there's you a little bit of mechanical weathering going on too. Now if we take that fluvial system and look a little bit further up into mountain streams, so these are streams in the mountains, then they can empty out onto alluvial fans, or they can just shallow out and form fluvial systems like we saw earlier. So these are all sort of tied together. The mountain streams are swift and carry large clasts. When the stream slows down, the gravels are deposited and sand or silt is carried further and further downstream. So these deposits tend to form breccias, sometimes conglomerates if they've been rounded off just enough, or sandstones. Shallow marine settings can either be clastic or carbonate. A clastic environment happens where rivers meet the shoreline and form deltas. This is going to give you really fine-grained silt being deposited, so things like shale and siltstone. The carbonate marine setting has little terrigenous input, so that means sediment from land. So there's not much coming in from land, so that marine life is what actually tends to form rocks like limestone. And there's a beautiful coral reef example, and that is a shot of the Kaibab limestone that caps the rim of the Grand Canyon. Now, coastal environments are going to cover a whole lot of different things. So you can have marshes with organic rich mud, a lot of even coals being formed here, really sandy bars. You can have delta faces, you've got turbidites coming off. Then out here you've got really deep water, mud and silt. Once you move out past kind of where the big stuff's deposited. So there's a lot of different things going on in a coastal environment. Now here's one of my favorite examples of some sedimentary rocks that we can figure out the environment by looking at the rock. So for instance, here's a shot from Mars. If you look, there's a lovely example of what looks to be riverine channels. This is the edge of a crater where one of the little rovers hung out for a very long time. And if you look real closely, you can actually see cross beds in that sandstone. So that means that those rocks were formed in big sand dunes, and we see sand dunes that are actually active on Mars right now. So that's not super surprising. But what is a little bit more surprising is this guy. Because this guy looks a whole lot like, hold on, let's go back, that guy, doesn't it? Yeah, so this has actually been interpreted to be an alluvial fan where the water is coming down off of the edge of a crater, a rim of a crater, and onto the flat bottom crater floor. And even here you can see the distributary channels where that water actually flowed out, which is pretty gnarly. And we know that Mars has conglomerates and breccias. This is a shot of a conglomerate that was actually discovered not too very long ago. So actually know these alluvial fans occur because this is actually from an alluvial fan in one of those craters. Now what's interesting is we have what's called a sedimentary facies. So this is a set of different rocks that tend to form near each other. So for instance, in a coastal setting, we're going to have sandstone along the beach. Once that sand settles out further than that, you have shale, the really fine stuff that makes it further out. And then you get past that where no terrigenous material is landing and you have limestone. These facies are really, really sensitive to changes in the water level. So if the sea level were to say rise, what would happen is that facies would move further up kind of to what's inland right now, and you have limestone being deposited on the shale, and shale being deposited on the sandstone, and sandstone being deposited further back. If sea level were to drop, that facies moves outward, so that you'll have sandstone being deposited on top of the shale and shale on top of the limestone. This is a great way to look at how sea level changes. So if the shoreline migrates inland where sea level rises, we call this a transgression. But if sea level falls and the coast migrates seaward, we call this a regression. Now we can track the changes in sea level on big scales over very long periods of time, and the rocks of the Grand Canyon are a beautiful example of sea level rising and falling.